In today's video, we're going to work through an example of essentially time evolution in our infinite well system. Uh, one of the potentials we've solved in the position representation over the last few videos. Um, so let's start. We're going to imagine we have a particle in an infinite potential well that's given by this wave function. And our essential question is, what is that wave function as a function of time? At some later time, what is that wave function going to be? And then once we have that, we can then calculate the probabilities of, a certain energy measurement or a certain position measurement or things like that. So we're going to just essentially in this video work through that example. It's very similar to an example in the textbook. They walk through the same sort of thing, but with a different initial potential or a different initial wave function. So in this video, you can also follow along in the textbook's example to sort of get a handle of this, right? The first thing we're going to want to do here is normalize this. We don't know what that A value is, right? So we're going to need that if we're going to actually get some numbers out of all this in the end. So to normalize this, if you recall, the normalization condition in bracket notation was just the inner product of any state function with itself is going to give us 1. And in the position representation, this meant that if I integrate the wave function over all space, so from negative infinity to infinity, the complex conjugate of that wave function times the wave function, that's going to be equal to 1, right? So this is, again, in the position representation. Now, in our infinite potential well, if you recall, we have a well that looks like this from 0 to L. This region was the only region where our wave function was finite. So this integral from negative infinity to 0 is just going to be 0 because everything we're integrating over 0. Likewise from L to infinity. So we're just going to integrate from 0 to L. And we're going to integrate our wave function. Since this is all, everything in here is real, it's just going to be this thing squared. So we end up with A squared times x over L cubed, minus 2 times x over L squared plus x over L all squared dx, right? And so this is all going to be equal to 1 because that's the normalization condition. So normalizing this amounts to just doing kind of a somewhat tedious integral, but it's an integral we should all be able to do. This is going to be a squared times the integral from 0 to L of all of these terms. Once we take the square of all this, it ends up being x over L to the 6 minus 4x over L to the 5th plus, am I doing this right? Yeah, 6x over L to the 4th minus 4x over L to the 3rd plus x over L squared dx. We want to do the integral of that. And again, this is just going to be a squared. Doing those integrals ends up, again, we should all be familiar with this, 7 over L to the 6th minus 4x to the 6 over 6L to the 5th, 6x to the 5. This is riveting stuff. I know, I'm sorry. L to the 3. And finally, x to the 3 over 3L squared from 0 to L. Rather than bore you with me writing this all out, when you put in the limits on this, obviously the 0, these are all just 0. The L comes to L. Hopefully you can all do this on your own, but this ends up being a squared L over 105. If you notice, like this L to the 7 is going to cancel this. All of these have an x to a power greater than the one below it, so the L factors out. This all equals 1, which means that our sort of normalization constant is going to be square root of 105 divided by the square root of L, right? Or written a little neater than that over L. So we've solved for A. That's pretty straightforward. Might be a little tedious to do all the expansions and all that, but or at least tedious to watch me do it. We can get through that. Now that we actually have our wave function, right? We have the full thing. We know the value of A. We can go on to the next step in how do we solve for time evolution, right? If you recall, the process that we've been using all semester since we first covered time evolution was the first step is take your wave function at t equals 0, which is what's given up here, um, and expand that in the energy eigenbases, right? So this was um, our take our wave function at t equals 0 and basically multiply it by the identity operator, which thanks to completeness looks like this. That's our this is the identity operator times that wave function, and this gives us the wave function expanded in that energy eigenbases. Where these coefficients here, this is just a linear combination of our energy eigenvalues. These C sub n's are equal to the projection of the wave function onto those energy eigenvectors. Right? So we know our energy eigenfunctions for the infinite square well, so we can figure this out, right? So our energy eigenvalues, energy eigenvectors, I should say, if you recall from a few videos ago, was square root 2 over L sine of n pi over L times x. These were the energy eigenfunctions for our infinite square well, right? And we're looking to sort out what are these coefficients in that linear expansion we just talked about. They're going to be equal to En times that wave function. And if we do that in the position representation, this is an integral over all space of the complex conjugate of that wave function, the energy eigenfunction, times our wave function with respect to x. So again, with the limits on this being that both of these are only have non-zero values inside the well, we're only going to integrate from 0 to L, and it's going to be this integral. We're going to integrate from 0 to L of 2 over L all square rooted sine n pi over L times x is equal to that A that we just had, 105 over L times x over L cubed minus 2x over L squared plus x over L that times dx. So again, what we have is our wave function and our energy eigenfunction there. And we're just integrating over all space, but since that's only finite in the well, we're integrating over the well. Just expanding this out, we can pull out that 210 over L, and now we're going to integrate from 0 to L, and this is going to look like x cubed sine n pi over L times x all over L cubed minus 2x squared sine n pi over L x over L squared plus x sine n pi over L x over L dx. Right, so we essentially have three integrals that we have to do. We can split this up, integral 1, integral 2, and integral 3. And again, much like the normalization stuff, doing these integrals might take a bit of work, might take some time, but we should all be able to trudge through this and sort it out. And this is, again, just because I've scrolled it off the screen, what we're calculating for the CN, those the coefficients of that linear expansion of our wave function in the energy eigenbases. So let's just work through those integrals. All right. So the first integral we have here, integral 1, is going to be the integral from 0 to L of x cubed sine. I'm going to just write this as kx because I don't want to write all those constants, dx, and I'm going to bring that 1 over L cubed out front. Right. So how do we do that integral? Well, easiest way is just look up that x cubed sine kx from an integral table. I'm not going to go through how to solve that from scratch, but we end up with 1 over L cubed. That integral, if you look up x cubed sine kx, where k is some constant, ends up being equal to 3x squared over k squared minus 6 over k to the fourth times sine kx plus 6x over k cubed minus x cubed over k times cosine kx. And we evaluate that from 0 to L. And again, all I really did is I looked up how to integrate that in a table of integrals. I used Sham's table of integrals. There are a million out there. You could probably just Google what the result of that integral is. Or if you're fresh out of 346 or Calc 3 or wherever you covered how to do these, you could go through some brute force and try to do it on your own. One thing we want to notice that makes this life a lot easier, at both the limits, if we plug in L, sine, remember k is equal to n pi over L. So k times L is going to be some multiple of pi, which makes that 0, and sine of 0 is 0. So this term's 0 at both the limits. We can ignore it. So when we plug in those limits, we end up with this integral being 1 over L cubed times imposing L there, we have 6L over n pi over L cubed minus L cubed over n pi over L times cosine of n pi. This is actually -1 to the n, right? If we look at cosine, looks like this at pi, 2 pi, 3 pi. As we go, if n, at n pi, this is going to be plus or minus 1, depending on whether n is even or odd. So it's -1. That's not equal to, but it's -1 to the n. And then, so now if we impose the other limit, the 0, this all ends up just being 0, right? All those terms out front are 0. So simplifying this, we end up with 1 over L cubed 6L to the fourth over n pi cubed minus L to the fourth over n pi. And we'll just multiply that whole thing by n pi squared over n pi squared. So we have the common denominator. And this times -1 to the n. So if we want to solve this, we're going to have two different terms. There's going to be, if n is an odd integer, we have that Cn is, not that Cn, sorry, this first integral in the Cn has an odd solution equal to 1 over, L over n pi cubed, and if n's odd, this is just going to be multiplied by -1. So this ends up being n pi squared minus 6, right? I factored out this n pi cubed here, um, and that's what we get. If n is even, this ends up being slightly different. It's just this -1 is now just a 1. So we just change the order of what we had here, right? Still n pi L, sorry, divided by n pi cubed times 6 minus n pi squared. So those are the results of our first integral of our three, if we scroll back up here. So we've done this one. Now, if the next integral I'm going to do, integral number 2. So if we scroll down here, I'll switch colors up just so we can. So let's just pound through that integral, right? So that integral is integral from 0 to L, 2x squared sine kx dx, 1 over L squared. Again, pulling out that 2, I end up with 2 over L squared. And if I evaluate that integral, I looked it up in Shams, what we end up with is, where was I? 2x sine kx over k squared minus or plus 2 over k cubed minus x squared over k times cosine kx. Evaluated at our limits from 0 to L. Just like with the previous integral, that sine term is 0 at both limits. So this ends up being 2 over L. If opposing the limits on the term that's remaining, we have 2 over n pi over L cubed minus L squared over n pi over L. And that cosine term, again, is just that -1 to the n when it's evaluated at L. This 0 limit doesn't actually disappear because this term here doesn't have that x in it. So we end up still having this 2 over n pi over L cubed term here. Cosine of 0 is 1, so that just stays like that. All right, so simplifying this a bit, this is 2 over L. This ends up being 2L cubed over n pi cubed minus L cubed. I'm going to give them the common denominator, so multiply by n pi squared to make this n pi cubed on the bottom. This is going to be -1 to the n still, minus 2L cubed over n pi cubed. All right, factoring out this n pi cubed and the L cubed, this is squared, my bad. We can simplify this a lot. We end up with 2L over n pi cubed multiplied by 2 minus n pi squared, that whole term divided by times -1 to the n minus 2. And we get this. Again, they're going to have two different solutions depending on whether n is odd or even. So n odd, this simplifies to 2L over n pi cubed. If n is odd, these are, these signs get switched because that's a -1. The -2 and the -2 ends up becoming a -4. And we end up with n pi squared minus 4. And if n is even, we end up, this whole thing is equal to just -2 L over n pi cubed times n pi squared. These twos cancel, and that pulled out. So again, here is our solution to the second integral we have. So again, scrolling up, we are now left with just this one, the third one. Again, same sort of thing. Let's just brute force walk through it. 3, integrating from 0 to L, 1 over L, x sine kx dx, which ends up being 1 over L sine kx over k squared minus x cosine kx over k. Evaluated from 0 to L. Sine term at both limits is 0, so we quite quickly just get 1 over L times negative L times that cosine is negative 1 to the n over n pi over L. And then this 0 limit just makes that 0. So simplifying this, the L comes up. We end up with, let's just do the odd solution. If this is odd, we end up with L times n pi squared over n pi cubed. I've again, obviously with the other integrals, they add that common n pi cubed term in the denominator, so I've just done the same thing here. And for the even terms, this integral ends up just being negative, the same thing. So we've sorted out all three of those integrals, plugging them back in here and acknowledging that the second one is multiplied by this negative sign. We've essentially, minus some simplifications, sorted out what our CNs are going to be. And we're going to have two solutions, for odd and for even, right? So if we plug in the odd terms, we have that 210 divided by L sticking out front. And our first integral for the odd ones was this n pi squared minus 6 all over n pi cubed. The second one is minus what we had for it, 2L over n pi cubed, n pi squared minus 4. And that last one we just did, n pi squared over n pi cubed. Simplifying this minus 2L, and basically the minus 2L n pi squared term here is going to cancel. So this term is going to cancel with this term and this term. And this simplifies a lot to 2 times root 210 over n pi cubed. That's Cn for the odd ends. That's what we get for that. If we do the same thing for the evens, Cn even, this integral become adding all those integrals into what we had gives L 6 minus n pi squared over cubed plus 2L pi cubed. Again, we're going to have a bunch of simplifications with things canceling, but this ends up being 6 times root 210 over n pi cubed. So this is our Cn for even ends. So those are our two solutions. It was, tedious to kind of go through that. It was probably worse just watching me go through it, but I think it's good that you actually do go through this because you're going to have to show that you can. But we figured out the coefficients in that linear expansion in our energy eigenbases, right? So let's think back to what the whole point of all this was. If we go way back up here, we have our we have our initial wave function. This can be written in terms of a linear expansion, and we've just figured out what those functions are, right? So scrolling down here, what we've just done is the first step in our time independence, uh, time dependence rather. We've taken, we know that that wave function can be written this way as a linear combination of all the energy eigenvalues. We've just calculated what those CNs are. So in the position representation, we know that psi of x at t equals 0, it can now be written as sum over n, these CNs we just calculated, times our energy eigenfunctions that we figured out when we solved for the infinite potential well, right? And summing over all n's. And if we want to look at what those CNs actually are, if you take n equals 1, n equals 2, and that, and plug them in, some of the values we get are C1 is equal to 0.9347, et cetera, et cetera. These actually make sense, though, if you think about it. If I plot uh, these values, if I plot that initial wave function in my well, it looks like this. And you'll notice, if you recall, our energy eigenfunctions, the first one looked like this, the second one was that sign, the third one was like this. This wave function, that initial wave function of ours, looks a lot like the the first energy eigenfunction. So we would expect that amplitude, the coefficient for that term, to be quite large. It's just kind of skewed a bit to the left in that, so we see much smaller amplitudes for all the other ones. And you can kind of get a sort of intuition for what you expect the amplitudes of those coefficients to be by looking at these closer that way. All right, so now that we have our uh, wave function at t equals 0 expanded in the energy eigenbasis, it's just a matter now of finding out what our wave function is as a function of time. And to do that, it's pretty trivial now. It's the same sum over Cn in the energy eigenbasis with those CNs we just calculated. We just have to add those phase energy dependent phases to that expansion. And now we have our wave function as a function of time by including that. We know the ENs, those energies, from when we solved the eigenvalue equation a few lectures ago. If you remember that, those were the energy eigenvalues for our infinite square well potential. We have those, so we know the phases, we know the energy eigenvalues, and in this video, we just calculated those CNs. So we have our wave function as a function of time. We can then use this to calculate the probabilities of whatever we want. The sort of straightforward probability we can do is what's the probability of measuring that system in some energy eigenstate, En, right? Postulate 4 tells us that this is just the projection of that state onto En all squared, right? We have this wave function in terms of our energy eigenbasis, so we can just replace that with our energy eigenbasis version of that state function. And this is really useful because we know that those energy eigenvectors are orthogonal or orthonormal, I should say. I'm actually going to change the index we're summing over so we don't get confused here. So these terms, this whole sum can come out. We can sum over m. We end up with C m e to the I e m t over h bar times that inner product, En times Em, all squared. This term is going to be, that's our Kronecker delta, Nm, where this is equal to 1 for n equal to m, 0 for n not equal to m. So this whole thing ends up simplifying to just Cn e to the I En t over h bar all squared. When we do this complex squaring, we do the complex conjugate of it. This ends up being just that amplitude Cn squared. We've calculated those Cn's. We've already done that. So we know that that's the probability. And it's the same probability as it would have been at t equals 0. We already have discussed this when we were using just the spin representation, and that the probability of measuring the system in a given energy state is going to be constant. But that's very different from saying that the state does not change with time, right? The probability of an energy measurement being constant does not imply that that wave function is not changing with time. So, yeah, we'll leave that here. In the next video, we'll go through how although the energy probability, the probability of measuring a given eigenenergy, it doesn't change with time. We'll look at other expectation values and other measurables and observables and see that they do in fact change with time.